Hello everyone, this is the second class of settlement. So today we'll talk about how to calculate the settlement. In the last class we have seen that the total settlement is the summation of immediate settlement SI and the consolidation settlement and the secondary consolidation settlement. So let's say that we have a structure on a ground surface, so that this structural weight will cause the additional stress on the ground surface, and that's going to cause the settlement on the ground surface. And in the sand, because the permeability is high, so as soon as you apply the load, the water will escape and it's going to cause the elastic deformation instantaneously. So in the sand and gravel, you have an instantaneous settlement. And the presence of water does not affect to this instantaneous settlement. But in the clay and the fine-grained sediment, because the permeability is low, when you squeeze it down, the water will need time to escape. So time-dependent settlement will occur with gradually increasing the sediment with the time. And it's called the consolidation sediment. And after the consolidation sediment, after all the water has been escaped, you have a creeping behavior, which is called as the secondary consolidation. And this secondary consolidation sediment is relatively small comparing to the consolidation sediment and minimal for the most clay, and there's very little for sand. So in this class, we'll mainly focus on the consolidation sediment and how to estimate the amount of the consolidation sediment occurring in the clay layer when you apply a certain amount of the stress. So we perform a consolidation test to estimate the consolidation sediment, and the purpose of this consolidation test is to calculate the void ratio change for a given loading delta sigma. And the procedure is this. So this is the site that you're interested in, that we want to build some structure on it. And you take the sample from the clay layer and take it to the lab and perform the consolidation settlement. And here the consolidation cell consists of the several parts, including the confining ring and the porous stone, and also the bath, the water bath. So first, you have a sample from the Shelby tube, and then you extrude the sample and trim it and place it within this confining ring. Then you place the porous stones at the bottom and the top of the specimen. And the purpose of this porous stone is to allow the water escape, water flow through the to the top and to the bottom. And you submerge this soil for about a certain amount of time, in general like 1 or 2 days, and then submerge it in the bath and apply the load and measure the height change. In this one-dimensional consolidation test, the assumption is the soil grains cannot move laterally, so the soil will compress vertically only. And this is the zero lateral strain condition, or it's called as the plane strain condition. And from this consolidation test, you obtain this kind of curve. So first you apply a certain amount of stress, maybe step loading 1, and then there will be a void ratio corresponding to that stress amount. Then you increase the stress. Then, because of the additional stress, the height will decrease, which means that you have decrease in void ratio. So you have another point, and you repeat the loading step 3 or 4, no, to the 6 steps, then you get the curve versus the effective stress, effective vertical stress. And from this curve, we can get the relation between voyage ratio and vertical effective stress. In general, the specimen size, the diameter, and the ratio of diameter to height is about 2.5 to 5. So here, if the height is about 1 inch, 2.5 centimeter, the diameter is about more than 5 centimeter. Typically, the height is 1 inch and diameter is larger than 2.5 inch. And sample preparation is you do the sampling usually using the Shelby tube, and you do the extrusion and trim in place into the confining ring. Then you're all set to perform the experiment. The procedure is like this. You apply the force, the dead load on the specimen, on the top of the specimen, and you can calculate the vertical effective stress from the load by dividing the area, the delta P over A. So then you have a total stress increase by delta sigma V prime, V, right? And because the clay is fully saturated, this total stress increase will transfer the water pressure increase, which is called the excess pore pressure. So then you have an initial excess pore pressure increase by delta P over A, which is the same amount of the total stress increase. Then you measure the sediment delta with time. So that can be done by measuring the displacement of the top cap, so that you can plot the height change. This is the height with time in the logarithmic scale, and so then you have this kind of a smooth curve. And at the height change, at the initial, as soon as you apply the delta P, you have a excess pore pressure increase by delta P over A. Here, note that the delta P is the force term, and this excess pore pressure will dissipate as time goes by because the water can escape, according to the permeability of the clay specimen. And then you have an endo-primary consolidation. At this point, you have a zero excess pore pressure, and the vertical effective stress will be the same with the vertical total stress. And in general, in the standard procedure, for a given loading, we wait about 24 hours. And you increase the load by 100%. So if the first step loading was delta P, then the second step is 2 times delta P, and third step is 4 times delta P, and fourth step is 8 times delta P. And you repeat these loading steps, normally 5 to 7 steps. And then you get the delta H, the height change for the effective stress applied. Then convert the H into the voyage ratio, then you can obtain the E and vertical effective stress relations, like this curve. The slope of this E versus vertical effective stress curve is called the compressibility, or this is called the compressibility. So at each loading time, you get the E versus logarithmic time curve, so E versus log T curve. And this can tell you how fast the settlement occurs, etc. And throughout the steps of the loading, you can get the E versus sigma V curve, the effective stress. Then this will tell you how much delta. So from this consolidation test, we can obtain the information about the time rate of the loading, and also we can get the information about the ultimate settlement, how much the settlement will occur for a given loading. So then, how can we change the height change to the void ratio? So how to convert the H to the void ratio? Because in clay, we are doing the fully saturated condition. So we assume that it's a fully saturated condition. So in the phase diagram, we have only the water phase and the solid phase. And it's a one-dimensional consolidation test, so the area remains constant. So the height change can be related to the void ratio and the volume directly, because the area stays constant. So initial void ratio, the definition of the void ratio is volume of void over the volume of solid. So this is the E naught. And if we convert it to the H, the height of each phase, the height of water and the height of solid, these two values will give you the initial void ratio. And H naught is the total height. Total height is the sum of the water height and the solid height. And here, HW naught, the water height, can be converted to the function of the void ratio and the solid height. So we get this equation. And during consolidation, the water is being expelled, so there's no change in solid volume. So total soil volume change is equal to the water volume change, because there's no change in solid volume, only the water is being expelled. So delta H, total height change, is the same with the water height change, delta HW. And void ratio change is defined as the void volume change over the solid volume. And because the soil volume change is the same with the water volume change, then we get this the second equation. Then from the first equation, here, this first equation, we can replace this HS with the H naught and the E naught, then we get this final equation. And this tells you that if you know the initial height of the sample, and if you measure the change in height of the sample, and if you know the void ratio of the sample, then you can convert it to the void ratio change. So E naught, H naught are known, and if the delta H is measured, delta E can be calculated. So that way you can plot the E versus sigma V prime curve. Right? And backwardly, if you know the void ratio change of the clay layer, and if you know the total thickness of the clay layer, then you can convert it to the settlement calculation. So here, say that let's assume that we know the void ratio change, then how much the settlement will occur. This equation tells you about that information. Here, the S, the settlement, is the negative change in height, and initial void ratio and the void ratio change and the total height of the clay, the initial thickness of the clay, can be converted to the settlement as. Just to clarify the symbol sign convention, delta, which means the change, is defined as the final state minus initial state. So if the delta H is negative, means that the volume contracts, so it settles. And if the delta H is larger than 0, so if it's a positive value, then the H expands, so that means the volume expansion. And if the delta E is larger than 0, so if it's a positive value, then it also says there is a volume expansion. And we can also define the volumetric strain, the epsilon V. The epsilon V is defined as the negative change in volume over the initial volume. So then negative delta H over H naught will be the volumetric strain for the one-dimensional consolidation test. So the epsilon V is defined as the minus delta E over 1 plus E naught. And here, if the epsilon V is a positive value, it means there's contraction. And if the epsilon V is negative value, less than 0, then it means the volume expansion occurred. So then, let's solve an example. The original thickness of a clay layer is 10 meter, and initial void ratio was 1.0 here. And after placement of a fill, a void ratio changed to 0.8. So that means the fill means that we apply the additional stress on this clay layer. Then the question is how much is the volumetric strain, the epsilon V, and how much is the settlement. So according to the equation, we can just follow the definition of the volumetric strain here. Epsilon V is defined as delta E over 1 plus E naught. So we can plug the number here. 1 plus 1.0. And the delta E is the final void ratio minus initial void ratio. So A minus 1.0. So then, how much is it? Minus 2 over minus 0.2. So we have a minus minus, it becomes the positive. So we have a 0.1. So volumetric strain is 0.1. And the settlement, we can also calculate the settlement using this equation. Let's use this equation. Minus delta E, 1 plus E naught times H naught. So then this is going to be same with the above the equation. 0.8 minus 1.0, 1 plus 1.0 times 10 meter. So it will be 0.1 times 10 meter, which is 1 meter. So this example tells you that if the void ratio change from 0.1 to 0.8 for whole clay layer, and when the clay layer is 10 meter thick, then the settlement will occur by 1 meter. Now, let's talk about elastic and the plastic deformation. So, imagine that we have a clay sample in a container, and we apply the vertical loading by delta sigma. And when the delta sigma is small, the clay, this flocculated clay, will resist this delta sigma with the only elastic deformation. So here, no fabric change occur and no particle rearrangement occur. So when you remove this delta sigma, this clay, it may have deformed a little bit, and then when you remove this delta sigma, then it's gonna go back to the original shape, and it's called the elastic deformation. And when you increase the delta sigma to a certain value, so now that the delta sigma is very large, then at some point this clay particle will move to cope with this large delta sigma. So that fabric will change and also the particle will move. Particle rearrangement. will occur. So then, when you remove this delta sigma, there will be still the permanent deformation, including this elastic deformation. Right? So, if you plot it in the chart here, the E versus sigma V prime graph, then when you have a large deformation, you have a small deformation, but this can be recoverable whenever you remove this delta sigma. And when you see some threshold value, then you have a plastic deformation which is permanent, and also the large deformation occurring together. So then now have more rapid change in void ratio for a given loading. And then what is the threshold stress causing this delta sigma? The plastic. So what is the threshold stress causing the plastic deformation? It's called the pre-consolidation stress, sigma p prime. So let's talk about the sigma p prime. And pre-consolidation stress, sigma p prime, is defined as the maximum vertical effective stress that the soil has ever experienced in the past. Because the soil has the memory effect, stress history affects the soil's behavior. For example, let's say that we have a soil in a container and we apply we pour the soil in a container. So the soil has never experienced any stress. Then we apply the vertical effective stress 100 kilopascal. So then this will settle, right, by this much. So the soil will deform. And now soil has experienced this 100 kilopascal. Right? And you unload it. And when you reload to 100 kilopascal, then this will the settlement will occur the same amount. Right? And in this case, the maximum vertical effective stress that the soil has experienced, the pre-consolidation stress sigma p, is 100 kilopascal. Right? And when you reload, and if sigma v, the current vertical effective stress, is less than p prime, let's say that you apply only like 50 kilopascal, then the elastic deformation only occurs. Why? Because the soil has remember that there was 100 kilopascal loading, so that they know how to resist this amount of the loading. Right? And if the sigma v prime, and when we increase this vertical effective stress, and if we exceed sigma p prime, then now it's a new level of stress. For example, if it says 200 kilopascal, then the maximum stress that the soil has experienced was the 100 kilopascal. So now the 200 kilopascal is too large for the soil particles. So then elastic and plastic deformation together. And once the settlement occurred, then the pre-consolidation stress, the maximum vertical effective stress, becomes 200 kilopascal. Okay? So then we can think about the compression curve, the void ratio versus sigma v prime curve, from the one-dimensional consolidation test. We'll have bilinear curve, which will look like this in ideal case. And here the threshold deflection point is sigma p prime, the pre-consolidation stress. And when we apply the stress below the sigma p prime, this is called a recompression curve. And when the vertical effective stress applied is larger than sigma p prime, the maximum vertical effective stress before in the past, then it's called a virgin compression curve. And the slope of this each curve is the compressibility. So this one CR, and this slope is called the recompression index, and this is called the compression index. And imagine that your current effective stress is somewhere here, and if you unload it or create another curve, it's not going to follow the virgin compression curve, because now the pre-consolidation stress becomes this point. So the slope of this rebound curve is called the swelling index, and this is called the rebound curve. Or swelling curve. Then this compression index and recompression index and swelling index can be defined as CR and CC and CS can be expressed as the void ratio change over vertical stress change. So in discrete form, delta E over delta log sigma V prime. So for example, for a compression curve, CC is minus delta E over delta E prime. So let's say that this is void ratio 2, and this is over 1, and this is void ratio 2, and this is sigma 1 prime, and this is sigma 2 prime. So there's a loading from sigma 1 to sigma 2, then minus E2 minus E1 over sigma 2 minus log sigma 1. Just note that this logarithmic function is base 10. Base 10. So then the equation becomes in general, as you can see, that the recompression index is much smaller than the compression index. So the 10th or the 5th of the compression index is the range of the recompression index. And the recompression index is quite similar to the swelling index, CR and the CS. Let's define the overconsolidation ratio, OCR. If the current effective stress, the vertical effective stress, is less than the pre-consolidation stress, and so is called as overconsolidated. So for example, if your stress is here, then your current effective stress is less than the sigma p prime. So your soil is overconsolidated state. and it's called the OC clay if it's clay, and this OC clay has very high stiffness, so it's just stiff and it's less compressible. And if the current vertical effective stress is the same with the sigma p prime, or we can say that if the current effective stress is the maximum vertical effective stress that the soil is being experienced, then it's called the normally consolidated clay, or the NC clay. So the over-consolidation ratio, in short, the OCR can be defined as the sigma p prime over the sigma v naught prime. So this sigma v naught prime is the current vertical effective stress, and the sigma p prime is the maximum vertical effective stress in the past. Okay. Let's solve the example. So initially the water table, groundwater table located here, the 5 meter deep, and at that time the total unit weight of the soil is 20 kilonewton per cubic meter, and at some point the groundwater table has risen up to the ground surface, to the position 2 here. And then what will be the OCR value and the sigma p prime? So then let's calculate the vertical effective stress at 5 meter deep at the time 1. Right? Here the vertical effective stress will be 5 meter times 20 kilonewton per cubic meter. So it's 100 kilonewton per square meter. So it's the vertical effective stress is 100 kilopascal. When the groundwater table has risen up to the ground surface at the time 2, then here groundwater table is here, so that we have to subtract the pore water pressure. Right? So sigma v prime will be 20 minus 10 kilonewton per cubic centimeter and 5 meter, so it becomes 50 kilopascal. So this is the current state, right? And this is the past. So the maximum vertical effective stress will be 100 kilopascal, and the over-consolidation ratio is sigma p prime over sigma v naught prime, so 100 over 50, so it becomes 2. So this soil, if it's clay, then it's the over-consolidated clay with the OCR value of 2. Okay, so now we can calculate the settlement for a single layer. As we talked before, in order to calculate the consolidation settlement, we need to know the initial thickness and the initial void ratio and the void ratio change. So we have to find out how much void ratio will change when we apply a certain amount of delta sigma. Right? So this will be caused by the structural weight of a structure. And how do we get this E versus sigma v prime curve? From consolidation test. And from consolidation test, ultimately we want to find this compression index and the recompression index, and also the sigma p prime. Then we can calculate the this delta E, the void ratio change, and from that we can calculate this consolidation settlement. So let's go back to the compression curve. the compression curve look like this. Sigma b prime. This is the logarithmic scale. Log and E, and ideally has a bilinear curve like this. And here, deflection point or threshold stress is called the pre-consolidation stress. And if the soil is normally consolidated, so that the current void ratio is here, let me use the other color, and as we apply, this is the sigma naught prime, and by this delta sigma has moved to this. And the final effective stress is sigma 1 prime. And then the void ratio is E1. So then the void ratio change, let's use this one. Void ratio change is E1 minus E naught is minus CC times log sigma 1 over sigma 0. Right? According to this equation. Right? Then from this void ratio change, you can plug into here. Then you will be able to calculate the settlement. But as you can see from this bilinear curve, there could be three cases. One, the current vertical effective stress is larger or the same with the sigma p prime. So the settlement occurs in this region. In this case, it's called the normally consolidated clay. And the second is if the sigma naught prime is less than sigma p prime, so that your initial void ratio and the vertical effective stress is here, and by this delta sigma, it may exceed the sigma p prime, or it may not exceed the sigma p prime. So you have two cases. So sigma naught plus delta sigma is that exceeds the pre-consolidation stress, or this one does not exceed the pre-consolidation stress. Okay. So in this curve, if this is the second case, and third case, and this is the first case, and first case will be from here to here. And the second case will be from here to somewhere here before the sigma p prime. And the third case will be from here to somewhere here exceeding the pre-consolidation stress. And we'll derive the equation for each case from 1 to 3 and how we can calculate this element. First, when we have a normally consolidated clay, NC clay, the current vertical effective stress is the same with the pre-consolidation stress. So the OCR is just 1. Okay? And initial vertical effective stress is sigma V naught prime and sigma I. And the final is sigma F prime, that's the initial value plus delta sigma. Then consolidation settlement is minus delta E over 1 plus E naught times H naught. And this, we can plug this equation, which is a function of the compression index. Then we'll have the final equation. So compression index times H naught over 1 plus E naught. So this is the original thickness, and the initial void ratio times the log base 10 times sigma V naught prime plus delta sigma over sigma V naught prime. Very straightforward. And the case that we have over-consolidated clay and the sigma F, the final effective stress, does not exceed the sigma P prime. In that case, it only changes over this recompression curve, so you just need to use this recompression index. So here the shape are the same. You can see CC and H naught over 1 plus C naught and log sigma F over sigma I, the initial stress, the final stress over initial stress. But the change is only the difference is they use the CC and here you use only CR, which is natural, right? Makes sense because in the OC clay they'll follow this recompression curve. But NC state, the normally consolidated clay, it's gonna follow the virgin compression curve, so you have to use different slope. So as the CR, the recompression index, is much smaller than the compression index, CC, so the settlement occur for a given loading, for the same amount of the loading, the settlement in the OC, over consolidated clay, will be much less than the settlement of the normally consolidated clay. And the last case, you start with the OC clay and the final effective stress exceeds the pre-consolidation stress, sigma P prime. So then you have to separate two stages. So from here to here, you calculate the voyage ratio change, and from here to here, you calculate the voyage ratio change too. So then, from using these two, you're gonna get the settlement corresponding to each voyage ratio change. So total voyage ratio change is the same with the delta E1 plus delta E2, and total settlement will be S1 plus S2. So and S1 is from voyage ratio change at this OC region, so from sigma V naught to sigma P prime, and the settlement 2, second settlement, is corresponding to the stress change from sigma P prime to final vertical effective stress here. So then you just sum up the two value, then you get the ultimate settlement. So here SC is first term from the recompression curve and the second term for the compression curve.